Hi friends, welcome back. Today we are going to see a very important topic which is signals and system in that Fourier series. Okay. So Fourier series, why we require Fourier series? Okay. Before going to Fourier series, there is a small topic which is the orthogonal signals. Once we complete that, that is actually the continuation which is going to give you Fourier series. That means suppose if you understand the orthogonality, then that is the basis for the Fourier series. Actually. Why? So first of all, try to understand orthogonality. Okay. So now we are discussing orthogonal signals. Orthogonal signals. Okay. You might heard this word orthogonal in so many times in your life. Let's say if I consider vectors, suppose in vectors let's say two vectors a bar and b bar are perpendicular, are orthogonal. When we can say their dot product is zero. Understood or not? So two vectors a bar and b bar are orthogonal if their dot product is equal to zero. Okay. Are orthogonal orthogonal if their dot product their dot product. So you might not know this actually. Dot product is also called as inner product. This is also called as inner product. Dot product or inner product is zero. Is zero. So a bar dot b bar is equal to zero. So whenever this condition is satisfied, then we can say a bar and b bar are orthogonal to each other. Okay. Now everybody knows this. From this, why we have to see this and what is the relevance for this to the signal source system? So let me tell you, suppose if you consider two dimension 2D, let's say this is x-axis, let's say this is y-axis. Now, if you consider a unit vector along x-axis as ax cap, if you consider a unit vector along y-axis as ay cap. Now, if you observe carefully, these two unit vectors ax cap and ay cap are orthogonal to each other or not? Of course, definitely they are orthogonal to each other. That means they are perpendicular to each other. Now, if I ask in two-dimension geometry, in two-dimension means we are having only this board. In this board, is there any other vector which is orthogonal to ax cap and ay cap simultaneously? Definitely answer is no. Some people will say z-axis, sir. No, z-axis is in the three dimension. I am not considering the three dimension here. I am considering only two dimension. In the two dimension, these two vectors are orthogonal to each other. There is no other vector which is orthogonal to both ax cap and ay. I hope you understood what I am trying to say. Now, so ax cap dot ay cap is equal to 0 and ax cap and ay cap are orthogonal to each other and there is no other vector which is orthogonal to both ax cap and ay cap. Is that clear? Now, let's say there is a vector a bar. Can I write a bar is something like 3ax cap plus 4ay cap? Can I write like this? Or we can write simply ax cap plus ay cap. So how this vector looks like? A bar vector. This is x-axis, this is y-axis. Ax cap plus ay cap is a vector which looks like this. This is a bar vector, which is passing through origin. I hope you understood. Now, if you understood clearly, any vector in two-dimension geometry can be represented by using ax cap and ay cap. So that means if you take any vector in the two-dimension geometry, any vector, it doesn't matter. So if you take any vector, all those vectors can be represented by using ax cap and ay cap or not? Definitely. Now I can say for two-dimension geometry, ax cap and ay cap are called as base vectors or sometimes called as bases. I hope you understood. So in the vector spaces, you might heard of this word base or basis or something like that. So I can simply say ax cap and ay cap are bases. Why they are bases? Because by using those vectors, I can represent any two-dimensional vector. That's the one thing. So I can simply say ax cap comma ay cap. This set is basis. This set is basis. So if I ask in three-dimension geometry, which one is the basis? Three-dimension. What is the basis actually? Ax cap, ay cap, az cap. So these vector group, that is ax cap, ay cap, az cap, are called as basis. And if you observe carefully, ax cap is perpendicular to ay cap is perpendicular to az cap is perpendicular to a. I can simply say all these three vectors are perpendicular to each other. Now, if I ask, is there any other vector which is orthogonal to these three vectors? Answer is no. Answer is no. So these are the three vectors which are orthogonal to each other. There is no other vector which is orthogonal to ax cap, ay cap, az cap. There is no such vector. That's why these became bases. Now, if I ask the necessary and sufficient condition to become a vector group as basis is definitely orthogonality. That means they must be orthogonal, and there should not be any other vector which is orthogonal to it. Then we can simply call that vector group is a base. And by using this basis, we can represent any other vector. I hope you understood. So that's what the meaning of basis. In the similar manner, suppose if I come to the signals topic. In the signals topic, if I say orthogonal signals. So if any two signals or some signals are orthogonal to them and there is no other signal which is orthogonal to them, that means those two are orthogonal and no other signal is orthogonal to that signal, those two signals, then definitely that signal group will form basis, and by using that basis I can represent so many signals. That is simply is nothing but the Fourier. And what is this? We will see that later. But for the time being, let's coming into the orthogonal signals. What do you mean by that? Here, orthogonal signals means definitely the inner product of the signals has to be zero. There we have seen inner product of the vector is nothing but the dot product. Now, in the signals topic, what do you mean by inner product? How can we say how can we define inner product? Suppose let's say real signals I am talking about. Suppose if the signals are real signals. Real signal. X1 of t is a real signal and X2 of t is another real signal, are orthogonal in the interval T1 to T2, if inner product is equal to 0. Inner product is equal to 0. What is the inner product for signals? It is not a dot product here because they are not the vectors, they are simply signals. So then what is the inner product here? It is integral T1 to T2, X1 of t multiplied with x2 of t dt. This is defined as inner product for the real signals. So if x1 of t, x2 of t are real signals, then this integration, that what is the integration actually? First we have to consider the product and we have to integrate from t1 to t2. Okay. So if I do that, this integration is called as inner product, and this inner product has to be 0. So I can simply say if inner product is 0, then we can call x1 of t and x2 of t are orthogonal in the interval t1 to t2. I hope it. Okay. Suppose if I give the same case for complex signals. What if the signals are complex? Let's x1 of t is a complex signal and x2 of t is a complex signal or orthogonal. Again the same thing. In the interval t1 to t2, t1 to t2. If inner product is equal to, so for a complex signal, what is the inner product? It is exactly similar to that of real signals, but a minor change is there. What is that minor change? Let's suppose if I consider integration from t1 to t2, x1 of t multiplied with x2 of t conjugate. It is not necessary to take the conjugate for second signal. You can take the conjugate for first signal also. So you have to take the conjugate for one signal, only one signal only. Okay. Then this integration represents the inner product, and this inner product has to be 0. Then if these conditions are satisfied for real signals, if the inner product is like this and if it is 0, for complex signals, if the inner product is defined as like this and if it is 0, then we can call those two signals x1 of t and x2 of t. Here x1 of t, x2 of t are orthogonal to each other. So this is a simple definition. Just remember, inner product has to be 0. For real signals, this is the inner product. For complex signals, this is the inner product. I hope you understand. Okay. So just make a note of it. I will give you some. Let's consider one question, example question. How the questions may come. x1 of t is equal to 2 between 0 less than t less than 1 is equal to 0 elsewhere. Okay. x2 of t is equal to 1 minus kt minus 5 less than t less than 5 and is equal to 0 elsewhere. If x1 of t and x2 of t are orthogonal to each other, during the time interval 0 to 1, obtain the constant k. Obtain the constant k. Okay. So they have given two signals x1 of t and x2 of t. they have defined between 0 and 1, and the signal is defined between -5 and +5. And they said that these two signals are orthogonal in the interval 0 to 1. So if it is the case, then what should be the value of k? So that those two signals are orthogonal to each other in the interval 0 to 1. Okay. So let's see. So what is the definition? If two signals are orthogonal in the interval, then their inner product has to be 0. So what is the inner product here? Inner product is integral 0 to 1. Why? They said it be between 0 to 1. What is x1 of t in the interval 0 to 1? That is simply 2 only. And what is the x2 of t in the interval 0 to 1? Yes, it is included in the -5 to +5. So it will become 1 minus kt dt. This inner product has to be 0. Then we can say those two signals are orthogonal. Okay. Now let's do the integration. 2 is a constant. For 1, t minus k t square by 2 between 0 and 1 is equal to 0. So 2 will go here, that will become 0. 1 minus k by 2 minus 0 is equal to 0. So simply k will become 2. So this is the k value. So that those two signals will become orthogonal to each other in the interval 0 to 1. Okay. Take it as quick as possible. Integration 0 to t sine omega naught t dt, where t is the period. What is this value? Suppose if you take any sinusoid, maybe sine or cos, it doesn't matter. If you consider one period and if you integrate it, so this is a positive area, this is a negative area, definitely this integration will become 0. This integration will become 0. That means if you integrate this, then we have to consider the positive area, we have to consider the negative area. If you observe carefully, how much is the positive area, that much is the negative area, and they are in the opposite sign, they will get cancelled each other. Finally, it will become 0. Okay. So I want to include something also here. Suppose if I place some constant k, will it make any difference? No, definitely. The amplitude will change, but still the area under the sine wave will become 0. Now, what I am trying to say is, suppose if I take integration 0 to t k sine omega naught t dt. This is also 0. Now, if I observe carefully, this k is a constant and this sine is a sine waveform. Now, I can treat them as this is a DC signal and this is a sine signal. Now, if you observe carefully, these two signals are getting multiplied with each other and I am integrating from 0 to t. Can I simply say k and sine omega naught t are orthogonal to each other in the interval 0 to t? I hope you understood. So I can simply say k and sine omega naught t are orthogonal. Are orthogonal. Okay. Now let's see some more example which is similar to this one. Integral 0 to t k cos omega naught t dt. This is also 0. That means k and cos omega naught t are orthogonal to each other. Integral 0 to t sin n omega naught t multiplied with sin m omega naught t dt. So sin A, sin B, we can use this formula that is a cos A plus B plus cos A minus B. Okay. So sorry, minus cos A minus B. So by using that formula, we can write this one into cos term. So I have already told you the cos waveform is also between 0 to t will become 0. Now, if you observe carefully, this will become 0. This integration will become 0 or t by 2. When m is equal to n, sorry, m is not equal to n, this integration will become 0. If m is equal to n, this will become t by 2. Why? Suppose let's say both m value n value is equal to 1. Then what will happen? It is sine square omega naught t. Sine square omega naught t can be written as, suppose if m is equal to n is equal to 1, then the integration 0 to t. This can be written as integral 0 to t 1 minus cos 2 omega naught t by 2 dt. So here this integration having two parts, 1 by 2 and cos 2 omega naught t by 2. So this cos value between 0 to t will become 0. Finally this is t by 2. So from that I can conclude that this value will become 0 or this value will become t by 2. It's depending on the m value and n value, whether they are equal or unequal. I hope you understand. Okay. So this is not necessary, just remember the result. In the similar manner, I can write integral 0 to t cos n omega naught t cos m omega naught. This result also the same way. It can be 0 or t by 2 depending on m value, n value. M is not equal to n here. M is equal to n. In the similar way, another result, integral 0 to t sin n omega naught t cos m omega naught t. So here, suppose if I consider one signal as sine, another signal as cos, there is no need to check whether the m value, n value are equal or unequal. There is no need for that. We can simply write this value is equal to 0 for all values of m and n. That means sine wave and cos wave are always orthogonal to each other. So there is no condition m is equal to n or m is not equal to n. So there is no such condition. I can directly say its value is equal to 0. So can I simply say this set sin n omega naught t and cos m omega naught t will become basis? Why? Because they are orthogonal to each other and there is no other signal which is orthogonal to them. Some people will comment that, sir, k is orthogonal to cos, k is orthogonal to sine. So there is another signal. Yes, but remember that cos itself is having the k. Why? Suppose if m value is equal to 0, then this will become constant or not. So constant itself is there in terms of, constant is there in the cos wave itself. I hope you understood what I am trying to say. So I can simply say sine wave and cos wave will become basis. I hope you understood. So I can simply say sine n omega naught t, comma cos m omega naught. This set will become base, or we can say base signal set. Base signal set or base signal base signal set. You have to compare them. E power j n omega naught t and e power j m omega naught. So what is the condition to say these two signals are orthogonal to each other? So first we have to check inner product. inner. What is the inner product actually? Integration over a period e power jn omega naught multiplied with e power jm omega naught t. So this has to be 0. But there is a mistake in it. You tell me. What is the mistake I have done here? Okay, intentionally I have made a mistake here. So I said this inner product. It is not the inner product. Why? So if you observe carefully, these two signals are complex signals. What did I told you? If it is a complex signal, definitely we have to take the conjugate for one of the signal or not. Then in this case, I haven't considered the conjugate. So we have to consider the conjugate. So how can we say that? So that means we have to take the conjugate. So that means this is equal to 0 to t e power j. This will become minus. So n minus m omega naught t. So because it is a periodic signal again, so it will become maybe 0 or it may become t. Suppose n is equal to m, this value will become 1. So if its value will become 1, then what is the integration value? That will go to t. So its value is equal to m not equal to n, then it is 0. If m is equal to n, then its value is equal to t. Now let's see, very important conclusion what I have to draw here. Let's see, in this case n is not equal to m orthogonal, n is not equal to m orthogonal. Here n is not equal to m orthogonal. If n is equal to m orthogonal, so actually what is the common here? If n is not equal to m, n is not equal to m, n is not equal to m, definitely they are orthogonal to each other. Yeah, in this case, if n is equal to m also is going to give you 0 case. But I am simply asking, if n is not equal to m, then definitely these signals are orthogonal. Clear? In the same way, for complex exponentials also, they will become orthogonal if m is not equal to. Now, listen carefully what I am trying to say. What is omega naught indicate? Fundamental frequency. Then what is n omega naught indicate? So it is m and n are nothing but the integers. What is the integer multiple of fundamental frequency indicate? Simple words, harmonic. What is that? Harmonic. So I can simply say, if you consider sine, cos, with different harmonics means different integer multiples of omega. That means n value, m value is not equal, then we can say they are different harmonics. I hope understood. So if omega naught is there, that is a fundamental frequency. If n omega naught is there, so that is called as harmonic. So if n is not equal to m, they are called as different harmonics. They are not the same harmonics, they are the different harmonics. So I can conclude that sine waves, cosine waves are, we can say, complex exponentials are orthogonal if they are different harmonics. I hope you understood. So this is the conclusion point what I am trying to say. So let's see. I am writing that conclusion point here. Sine or cos waves of different harmonics are orthogonal to each other. So we have to underline this different harmonics. That is important. Next. Complex exponential of different harmonics are orthogonal to each other. Are orthogonal to each other. Here also different harmonics. Here first we have to understand the definition of harmonic frequency. What is the definition of harmonics? So the integer multiple of fundamental frequency fundamental frequency. So it is like a n omega naught or n f naught, like that, n f naught. So if you consider omega naught, n omega naught, if you consider f naught, that is a direct absolute frequency, then it is n f naught. Okay. Integer multiple of fundamental frequency are called as harmonics. Take it. What is the application of Fourier series? That means why we require Fourier series. What is the importance of Fourier series? Okay. Let's see. You can get the answer. What is the example I am taking? Suppose, first example, if I take a DC voltage source, let's say 10 volts. A resistor is connected and a inductor is connected. So let's say 1 ohm, 1 Henry. They want to calculate how much is the current flowing through it. Okay. So first what we do actually, so to analyze any network, first we have to observe what is the source we are having. What is the source we are having? Is a 10 volt DC voltage. Okay. So it is a DC voltage source. Because it is a DC voltage source, we have to do the DC analysis. In the DC analysis, so what will happen to the inductor at a steady state? This will become short circuit. So finally, I can represent this network as 10 volt, 1 ohm, short circuit. Then the current can be directly calculated as I is equal to 10 by 1, that is 10 amps. Is that clear? So this is called as DC analysis. DC analysis. Okay, everybody knows it. Now, what if they have given the same network, one Henry, 1 ohm, but instead of they have given a sinusoidal voltage source, let's say 10 cos t plus, okay, cos t, 10 cos t, they have given. They want to calculate what is the current. What is the current? Now, in the previous case, they have given DC voltage source, then we have applied the DC analysis. But in this case, they have given an alternating voltage, or we could say AC signal. So if it is a AC signal, then we have to perform AC analysis, sometimes called as phasor analysis. So first we have to convert the voltage source into phasor, 10 at an angle 0 degrees, and 1 ohm will become 1 ohm only, and here the inductor cannot be short circuited. It can be represented as J omega L. So J omega value 1, so L value 1, so J1. Then what is the current phasor I? So actually whatever we have performed is nothing but the phasor analysis. Phasor analysis. Then what is the current phasor I? I is equal to 10 at an angle 0 degrees by 1 plus J1. So finally 10 by root 2 at an angle minus 45. So this is what we got. So I am not doing any network analysis here. So just try to remember what I am doing actually. So if it is a DC input or DC source, then we have to perform the DC analysis. If it is a AC signal, then we have to go with the phasor analysis. So everything is nice. Now the question is, again the same circuit. 1 ohm, 1 Henry. The input voltage is given like here V of t is given like this. A square wave 0, let's say t by 2 t a something like that with respect. So if you observe carefully, if a DC signal is given, we can do the DC analysis. If AC signal is given, then we can do the phasor analysis. But it is not a DC signal, it is not a sinusoidal signal. Then it is a periodic signal, but it is non-sinusoidal. I hope you understood what I am trying to say. So it is a periodic non-sinusoidal. Then what is the analysis we have to do? We don't have any analysis technique. So it is not a DC signal, so to apply the DC analysis. It is not a AC signal, to apply the phasor analysis. Then what we can do? We can do one thing. By using the Fourier series, I can convert this non-sinusoidal periodic signal into sinusoid. I can do that. That is the beauty of Fourier series. By using Fourier series, we can convert a non-sinusoidal periodic signal into a sinusoidal periodic signal. Then we can use the AC analysis technique. What do you mean by that? So let's see. I can write, I'm directly writing this one. So after once we enter into the Fourier series completely, by completion of Fourier series, you can understand how I could write the Fourier series for this V of t directly. So for the time being, so just understand or just note down what I am writing here for V of t. V of t is equal to a by 2 plus 2a by pi, 2a by pi sine omega naught t plus 2a by 3 pi sine 3 omega naught t plus and so on. Once I can write V of t like this, so this is called as Fourier series. So this is nothing but the Fourier series. So here the analysis what we use is Fourier series. So why, by using the Fourier series, if I could express this non-sinusoidal periodic signal in terms of sine wave, then it will become very easy. How? So first I can go with the a by 2. So if I apply a by 2, then I know this is nothing but the DC signal. So I can perform the DC analysis and I can find out the what is the current in it. Next, I can apply this signal here, then we can get a current by using the phasor analysis. I can apply the next signal, I can apply the next signal like that. So I can get some responses here and I can add those responses by applying the principle called as superposition. So by applying the superposition, I can find out the total response by adding all the responses. So this is where Fourier series having very much application. So I hope you understood what I'm trying to do. So if it is a DC input, I can go with the DC analysis. If it is a AC input, I can go with the AC analysis. What if it is a periodic signal but non-sinusoidal? Then we don't have any analysis technique. Then we have to apply the Fourier series. So I hope you understood. By applying the Fourier series, I can convert a non-sinusoidal periodic signal into sinusoidal signal. Once we understand how to write that, then the analysis technique is as simple as that by applying the superposition theorem. What do you mean by that? First, we can apply the DC signal, then we can get the output. Next, we will apply this signal, then we can get the output. Then we will apply this signal, then we can get the output. Then we can sum them by applying the superposition theorem to get the final answer. I hope understood. Okay, take it. Not much important, but just you have to understand that where the application here in network analysis, if the input is a non-sinusoidal periodic signal, then definitely Fourier series will help you a lot how to analyze the network. I hope you understood.